In problem 8, find the dimensions of the rectangle with the largest area. Okay, here's the objective function with the largest area that can be inscribed in a closed region bounded by x-axis and y-axis graph for the graph of y equals to 8 minus x power 3. So here's the constraint. Okay, so area equals to x times y. Here the constraint is in y equals to 8 minus x power 3. So a equals to x times 8 minus x power 3. We can write it as 8x minus x power 4. Differentiate to find the critical points. A dash will be 8 minus 4x power 3 equal to 0. Then x power 3 equals to x power 3 equals to 2, which means that in x equals to the cubic root of 2. Find the point x and y on the graph y equals to root x. This point is the nearest to the point 4 and 0. X equal 4, y equal to 0. Here, this y equals to root x. Here, this is the point 4 and 0 that he is talking about. 4 and 0. So he is looking for this point, x and y. As he is talking about the nearest to the point, then he is talking about the minimum distance. Then it's clear in this case that the objective function is the distance function. So d equals to root of x minus 4 squared plus y minus 0 squared. We can consider the square of this distance function as an objective function. This is because that in this distance function is increasing. Then f of x y equals to x minus 4 squared plus y squared. But here, this point is located on the curve y equals to root x. So square it, y squared will be x. Then replace this y squared by x. Then the modified objective function f of x modified will be x minus 4 squared plus x. Okay, to find the minimum distance, find the derivative of this function. F modified dash will be 2 times x minus 4 plus 1. Equate this by 0. Then 2x minus 8 plus 1 equal to 0. This leads to that in x equals to 3.5. Testing this point on f dash or f modified dash, you will get 3.5. Value before, you will get negative. Value after, you will get positive. So the coordinate of this point is at x equals to 3.5, then y equals to root 3.5. So the coordinate of this point is 3.5 and root 3.5. In problem 2, consider a rectangle of perimeter 12 inches. A cylinder has been formed by rotating this triangle about one of its edges. What are the dimensions of the rectangle that will result to a cylinder of maximum volume? So here we have a rectangle. Dimensions of the rectangle are x and y. So the perimeter 2x plus 2y equals to 12. Or in other form, in x plus y equals to 6. This is the constraint. This is the restriction. Okay, a cylinder has been formed by rotating this rectangle about one of the edges. Now, what are the dimensions of the rectangle that will result in a cylinder of maximum volume? Here, this is the objective function. Here, this is the objective function. Okay, so how come? Imagining that in this rectangle is rotating about one of the edges. Let's say this edge is y. So this means that in y is representing the height and x is representing the radius. So volume of that we want to maximize it is v. This is the objective function. Let's say the objective function. The objective function now is v that equals to pi r squared times h, which is here based on these dimensions. R is the radius by x squared times h is the height, y. So we need to maximize this function. Already here we have x plus y equals to 6, and we need to represent this objective function v as a function of one variable, x or y. So I think it's proper to replace y. So substitute with this y, then replacing y with 6 minus x. So the objective function now will be pi x squared times y, which is y minus 6 minus x. Or in other form, this is pi times 6x squared minus x power 3. Find v dash. To find the critical point, find v dash. So v dash will be pi times 12x minus 3x power 2 equated by 0. So we can factor x, then it's 12 minus 3x equal to 0. The product equal to 0. X equal to 0, which is physically not acceptable, or in x here equals to 4. The number line v dash, substitute in the derivative of the objective function, substitute with the value before 4 like 1, you will get positive. Value after 4, you will get negative. So it's positive, then negative. This means that in this point is a local maximum point. So this is x. But as in x plus y equals to 6 and x equals to 4, then y equals to 2. Then the maximum volume, V maximum, will be by x squared, which is 4 squared, times y, which is 2, the 32 pi. In problem 4, a right angle triangle whose hypotenuse is root 3 meters long is rotated about one of its sides to generate a right circular cone as shown in the figure. So find the radius and the height of the cone with the largest volume. Okay, so the largest volume is the objective function. The largest volume is the objective function, which is this function. Okay, but we are looking now for the constraint. Okay, the constraint is shown from this triangle r square plus h square. This equals to root 3 square, which is 3. So this is the constraint. And here this is the objective function. We need to maximize that in v equals to 1 over 3 by r square times h. Okay, so just substitute with this r square in the volume, then r square equals to 3 minus h square. 3 minus h square. And substitute with this r square in the objective function to represent the volume function purely as a function of h. So v equals to pi over 3 h times r square, which is 3 minus h square, which is pi over 3 times 3h minus h power 3. Differentiate this volume with respect to h to find the critical points. Here we have pi over 3, derivative of 3h, this is simply 3, derivative of h power 3, this 3h square. Okay, so and equate this v dash with 0. I think it's clear that in h will be 1. The number line for v dash, here we have 1. Substitute with a value before positive, substitute with a value after negative. So positive, negative, this means that in this point at h equals to 1, the function is maximum. So at h equals to 1, v is maximum. Now we need to find the r. R will be r squared equals to 3 minus 1 squared, which is 3 minus 1, which is 2. So r squared equals 2. R squared equals to 2, then r equals to root 2. So v maximum is pi over 3 r squared, which is root 2 squared, times h, which is 1. So at the end, it's 2 over 3 pi. In problem 7, a water tank in a small community is built in the shape of a right circular cylinder with a capacity 32k feet cube. The interior wall, the inside walls, and the floor of the tank must be cleaned and treated manually. Labor costs for cleaning these walls is twice as high as the cost of the cleaning of the floor. So find the radius and the height of the tank that minimizes the cleaning cost. Starting by the constraint. The constraint here is the volume of the tank, V, that equals to by r squared times h, by r squared times h. And this volume equals to 32k, 32,000 feet cube. This one. The cost of cleaning the tank is the objective function. This cost equals to costs for cleaning the walls plus cost for cleaning the floor. Okay, and he mentioned that in cost for cleaning the walls is twice as costs for cleaning the floors. So cost for cleaning the walls, let's call it area of the walls is by r square. So if we assume that in K is cost for cleaning 1 unit area is the cost for cleaning 1 feet square of the floor. So the total cost function will be the area of the walls is 2 by RH times 2k plus the area of the floor is pi r square times k. To find the critical points, we need first to represent this function in one variable. Here we have r and h, and here this only r. So we need to represent this function as a function of one variable using this relation for the constraint. H will be 32 thousandths divided by r square, and substitute with this h in the cost function. So the cost function will be, we can factor k out, 2 by r times h, which is 32 thousandths divided by r square plus r square, canceling r with 1 r, canceling with this 2 times 32, 64 thousandths. So the cost function will be k times 64 thousandths divided by r plus r square. Differentiating this cost function to find the critical points, c dash will be k constant, which is factored out, times derivative of the first term, the 64 thousandths divided by r square, the negative, plus r square, its derivative is 2 by r. So equating the c dash with 0, then we get that in 2 by r equals to 64,000 divided by r square. Or in other form, r power 3 equals to 32,000 divided by pi. Find the cubic root. So r in this case will be 21.7 feet. So this is r. H will be, already here we have a relation for the height with the radius. H will be 32,000 divided by r square. By times r square, which is 21.7 square, equals to, this is the value of h. The screen on the wall is 20 feet height and it's 10 feet above the floor. At what distance x from the front of the floor should you position yourself as a viewer? How far is your distance as a viewer from the wall to maximize the angle theta to make q is as large as possible? Okay, so here is the only variable that we have, x. The distance from the floor to the bottom of the screen, this is 10. The distance from the floor to the top of the screen, this is 30, which is 10 plus 20. So we need to maximize this angle. If we assume that in here we have an angle alpha and here is an angle beta, so theta that we need to maximize is beta minus alpha. From the geometry of the shape, tan alpha is the opposite, which is 10, divided by the adjacent, which is x. Tan beta is the opposite, which is 30, divided by the adjacent, which is x. So this means that in beta equals to tan inverse 30 over x. Alpha equals to tan inverse 10 over x. So theta will be beta, which is tan inverse 30 over x, minus alpha, which is tan inverse 10 over x. Tan inverse 30 over x minus tan inverse 10 over x. We need to maximize this function. We need to maximize this theta. So to maximize it, then find theta dash. Differentiate it. Theta dash would be derivative of tan inverse 30 over x, this one, plus 30 over x square times the derivative of what's inside, which is negative 30 over x square, minus derivative of tan inverse 10 over x, this is 1 plus 10 over x square times the derivative of what's inside, which is negative 10 divided by x square. To simplify the form of these functions, multiply by x square up and down. Then theta dash is negative 30 divided by x square plus 30 square, which is 900. Negative, it's positive. 10 divided by x square plus 100. This equal to 0, as we know. This to find the critical points. So now we can say that in the 10 divided by x square plus 100 equals to 30 divided by x square plus 900. After cross multiplication and simplifying the numerators, here we have 1, here we have 3. Then x square plus 900, this equals to 3 times x square plus 100. X square plus 900 equals to 3x square plus 300. So to solve, we get in 2x square equals to 600, which means that in x square equals to 300, or in other form, x equals to 10 root 3. Substitute in theta dash, number line, theta dash, 10 root 3, 17, about 17.4. Substitute the value before, positive substitute the value after, negative, increasing, decreasing. So at x equals to 10 root 3, we get theta maximum. And theta in this case will be beta, which is tan inverse 20 divided x, which is 10 root 3 minus tan inverse 10 divided by 10 root 3. Consider all triangles that are formed by the lines passing through the point 1 and 2 and both x and y axes. Triangles formed by the x and y axes, x-axis, y-axis, and the lines passing through the point 1 and 2. This is for the hypotenuse 1 and 2. Find the dimensions of the triangle with the shortest hypotenuse. Okay, so here this x-axis, this y-axis, this is the horizontal base, this is the vertical base. Okay, so the bases x and y axes, shortest hypotenuse. The hypotenuse is intersecting the x-axis at the points A and 0, intersecting the y-axis at the point 0 and B. So this means that in the length of the horizontal base is A, the length of the vertical base is B. It's requested to find A and B on condition that the hypotenuse, which is L squared equals to A squared plus B squared, is minimum. Okay, so he is looking for the shortest hypotenuse, this corresponding to minimum hypotenuse. So L square equals to A square plus B square. Or we can say that in the function, minimum function, it's requested here to minimize the function f of A and B equals to A square plus B square. Okay, but we need to find the relation between A and B. How come? The equation of this line, which is passing through the points 1 and 2. The general equation for this line is x over A plus y over B, and these A and B are intercepts with the x and y axes equals to 1. But at the same time, this line is passing through the point 1 and 2. So this means that in the point 1 and 2 is satisfying this point. So this means that in the point 1 and 2 satisfying the equation of this line. So for x equals 1 and y equals 2, this equals to 1. So 1 over A equals to 1 minus 2 over B, or in other form, 1 over A equals to B as a common factor. Here this is B minus 2. So A will be B divided by B minus 2. Then A will be B divided by B minus 2. Now substitute in the function f that equals to A squared plus B squared. A is B divided by B minus 2. B divided B squared divided by B minus 2. It's A squared plus B squared plus B squared. Now to find the critical points, find the derivative of this function. So f dash will be, for the first term, down square, B minus 2 power 4, up dash down, 2B times B minus 2 square, minus down dash up. Down dash is 2 times B minus 2 times the numerator, B square, plus derivative of B square, this 2B. Okay, from this step, we can simplify, cancel one of this B minus 2 and this B minus 2 with this B minus 2 power 4 to B minus 2 power 3. So f dash is 2b times b, this 2b square, minus 2b times negative 2 minus 4b, minus 2b square divided by b minus 2 power 3, plus 2b. 2b square minus 2b square. And we can factor 2b out, it's 2b, to get negative 2 divided by b minus 2 power 3, plus 1. For f dash, to find the critical points, we equate f dash by 0. Okay, so from this step, we have a product equal to 0. To be equal to 0 or this bracket equal to 0. B can be 0. This is not what of the physical solutions. So the bracket equal to 0. Then negative 2 divided by b minus 2 power 3 is the one equal to 0. b minus 2 power 3 plus 1, this equal to 0. So switching this fraction to the other side with the positive side, 2 divided by b minus 2 power 3, this equals to 1, which means that b minus 2 power 3 equals to 2. Cubic root for both sides, then b minus 2 equals to the cubic root of 2. Then b equals to 2 plus the cubic root of 2. The value is 3.26, nearly 3.26. So locating this b on the number line, here we have 3.26. Substitute with the value before and substitute with the value after. Substitute to the value before in f dash, you will get negative. Substitute to the value after, you will get positive. So this value 3.26 is local minimum. This value is a local minimum. Okay, so here this is B, 3.26. Substituting in this relation between A and B, we can find the value of A. Then 1 over A plus 2 over B. B is 3.26. This equals to 1. So A will be 2.59. So this means that the minimum hypotenuse is A square plus B square, which is 2.59 square plus B square, which is 3.26 power 2. In problem 5, find the dimensions, the radius and the height, the radius r and the height h for the cone with a maximum volume that can be inscribed, which is located in a sphere of radius 2. Here, this is the illustration shape for the cone inscribed in a sphere. This is the base of the cone. Now we need to identify what is the volume, which is the objective function, v, that equals to 1 over 3 pi r squared times h. And where is the constraint? The constraint here, we can get it from the right angle triangle. From this right angle triangle, this is the radius of the sphere, r, that equals to 2. Here we can recall this segment from the origin of the sphere to the base of the cone as y. And here this r small, this is the radius of the base of the cone. So we can say that in r square plus y square, this equals to r capital square, the radius of the sphere. R capital is 2 power 2, this is 4. Okay, and this h, this is the height of the cone. H here equals to the radius 2 plus the distance from the origin, or from the center of the sphere, the distance from the center of the sphere to the base of the cone, which is y. So v can be represented as pi over 3 times r square times h, which is 2 plus y. And we can rewrite this r square as 4 minus y square. The aim from this action is replacing this r square by 4 minus y square. So the volume now will be v equals to pi over 3 r square, this 4 minus y square, times 2 plus y. Then we have now the volume as a pure function of y. So it's requested now to find v dash. It's pi over 3 times, expand these two brackets. Expand these two brackets. 4 times 2, this is 8. 4 times y plus 4y, negative 2y squared minus y power 3. So find v dash. V dash will be pi over 3 constant as it is. Derivative of 8 is 0. Derivative of 4y is 4 minus 2y squared. Its derivative is minus 4y minus 3y power 2. Find the critical points by solving this equation. So here we have two values, roots for this equation, y equals to 1.5 or y equals to negative half. Physically, it's proper to take y as 1.5. Now, locating this y dimension of 1.5 on the number line for v dash, substitute to the value before, you will get positive. Substitute to the value after, you will get negative. So positive, then negative, which means that at y equals to 1.5, we have local maximum. Now this is y. From this y, we can find the r. Now this is y equal. From this y, we can find the r. Already here, r squared plus y squared equals to 4, or r squared equals to 4 minus y squared. R squared equals to 4 minus y squared, which is 1.5 power 2. So r in this case will be 1.32. And then h will be 2 plus 1.32, which is 3.32. Then the maximum volume in this case would be v equals to pi over 3 r squared, which is 1.32 power 2 times h, which is 3.32.